In this video, I would like to study the special case of what happens when you're taking the derivative of a function which is the inverse of another function. So by the end of today, we should review the definition and the properties of inverses, and we'll state the formula for the derivative of the inverse of the function x, and we'll use that formula in particular to find the derivatives of things like arcsine and arctangent, the inverse sine and inverse tangent functions. So let's review inverses of functions. Recall that a function f of x was invertible. In other words, a function f of x had an inverse if the function passed what was called a horizontal line test. The horizontal line test said any horizontal line will cross the graph in at most one location. So a function like e to the x, a J-shaped curve, was okay, because no matter what horizontal line you drew, that horizontal line never crossed the graph in more than one location. On the flip side, if you had something like a parabola would not pass the horizontal line test because this horizontal line, for example, crosses the graph in more than one location. This would be not invertible. This function would not have an inverse, whereas the function on the left side would be invertible. This would have an inverse. Now, in the case that your function f of x did have an inverse, that inverse got special notation to honor its relationship to the original function f of x. The inverse function was denoted by f with an exponent of -1 before the parentheses x. It's commonplace to have some functions which technically are not invertible, but if you restrict your attention to just a small portion of the graph, then it is invertible. For example, x squared. The full graph, x squared, does not pass the horizontal line test because a horizontal line would cross the graph in two places. But suppose that we restricted the graph so that we only had the right portion of x squared, only the portion where x was greater than or equal to 0. Then this function would pass the horizontal line test, and this function would have an inverse. And in particular, the inverse of this version of x squared is given by the square root of x. Likewise, a function like sine of x, because it has this sinusoidal periodic behavior, this fails the horizontal line test in a dramatic way. Any horizontal line would cross this graph in infinitely many positions. So the idea is only to consider x's from -π/2 to π/2. Now your graph does pass the horizontal line test, so this function is invertible, and we call f inverse of x arcsine. Now, what was the defining feature, the big important property of the inverse function? The defining feature of the inverse function was that, compared to the original function, f of x, the values of x and y were swapped. To give you an example, we have the function f of x equals e to the x. From its graph above, we saw that it is invertible. And the inverse of the function e to the x, the natural exponential, was given by its arch nemesis, the natural log. Exponential base e becomes log base e. Now if you compare the x and y values for the original function to the x and y values for the inverse function, you'll see that they're absolutely identical but flipped. For example, if you plug 0 into the exponential function, 1 is the result. But if you plug 1 into natural log, 0 is the result. If you plug 1 into the exponential, e is the result. But if you plug e into the natural log, 1 is the result. It's completely opposite. You can see this property manifest itself graphically as well. In blue, we have the graph of the original function e to the x. And in orange, we have the graph of the inverse function natural log of x. These two graphs are mirror images of each other across the diagonal line where x is equal to y. To get natural log from e to the x, you basically just swap the roles of x and y, which amounts to flipping the graph across the line where x is equal to y. Points on one graph show up as mirror images in points on the other graph. Here is 0, 1, and the sister point to that in natural log is 1, 0. X and y have swapped. 1, e, the sister point is e, 1. So x and y have still once again swapped. Now because there's such an interesting graphical relationship between the graph of e to the x and its inverse, it's natural to ask if there is a graphical relationship between the tangent lines of the original function and the tangent lines of the inverse function. For example, here in the graphs, I've added the tangent line to e to the x at the location where x is 1. And I've also drawn the tangent line at the sister point in natural log of x. I've drawn the tangent line to natural log at this location where y is 1 and x is e. Is there any relationship between the slopes of these two tangent lines? In other words, is there any relationship between the derivative of an original function and the derivative of its inverse? Now, if you're looking very closely at these equations in the bottom left, you may see something interesting. The slope of the pink tangent line, the slope of the tangent line to e to the x, is given by the number e, this number multiplied outside the parentheses here. The slope of the tangent line to natural log is 1 over e, the reciprocal of the slope of the pink tangent line. That turns out actually to be true in general. It's given by what we called rise over run. It's given by the difference in the two y values divided by the difference in the two x values. But when you change from f of x to its inverse, x and y swap values. And so as a result, when you change to the inverse, x gets moved to the top, y gets moved to the bottom, and the entire slope gets flipped upside down. So let's give the formula for the derivative of f inverse of x. If you want the derivative of f inverse of x, you find, as expected, a reciprocal. 1 over the derivative of the original function, but here's the hitch. In order to get the correct value, what do we have to plug in to the derivative function? We have to plug in f inverse of x. This is a little technicality that has to do with the fact that if you look at the two tangent lines in this picture, the two tangent lines are not quite located at exactly the same position. The pink tangent line is located at the position where x is equal to 1. But the mirror image, the yellow tangent line, is located at the position where the x is equal to e and the y is equal to 1. So it's the reciprocal of the derivative of the original function with f inverse plugged in. Let's find, and this is going to be interesting, let's find and completely simplify the derivative of inverse tangent using that formula. The first thing that I'm going to acknowledge is that inverse tangent, arctan, is the inverse of the function tan. And the derivative of tangent, f prime, is equal to, long ago we found that this was equal to secant squared. Now that is f prime with x plugged in. In order to fill in the blanks in this formula, I need f prime with f inverse plugged in. So let's take f prime, and instead of having x, let's plug in f inverse. Let's take secant squared, and instead of having secant squared of x, let's put in arctan. In order to find then the derivative of arctan, all I need to do is take the reciprocal of this quantity. Now here is where things get interesting. For once in our lives, we were actually asked to simplify this quantity. And at first glance, it may not seem like it actually can be simplified. But as a matter of fact, we can simplify this fraction dramatically. As a matter of fact, I claim that we can simplify this fraction so much that in the end, there will no longer be any trig functions at all. So I want you to pay attention to what we're doing here, because in the exercises I'm going to give you the opportunity to try this in the case of inverse cosine. So when trig functions are involved, there are usually one of two tools that you need to work with that situation. The first potential tool is the unit circle. And unit circles are especially great if you're working with situations where you have sine and cosine. But the other tool that can be used is the triangle, the right triangle in particular. I'm going to introduce an angle, which I'm going to nickname theta. Remember that arctan takes in values and produces angles, because tangent took in angles and produces values. In particular, the tangent of an angle was equivalent to the opposite side divided by the adjacent side in a right triangle, such as the one I've drawn here. So suppose that I specifically draw a triangle which has this angle theta in the bottom left. Such a triangle could have sides where the opposite side was equal to x and the adjacent side was equal to 1. Because then opposite divided by adjacent would be equal to x divided by 1, which, sure enough, is equal to x. So in this right triangle, if I have one leg that's x and one leg that's 1, what would the hypotenuse be? The hypotenuse, by Pythagorean theorem, would be the square root of 1 squared plus x squared. So what did I do? I nicknamed arctan theta. And then I built a right triangle which could reasonably have the angle theta in the bottom left corner. If theta was there, then one possibility for the two legs was x and 1. If I have x and 1, then opposite over adjacent, x divided by 1, would be equal to the x value that is output by tan of theta. So now, let's think about what secant of theta would be. For a right triangle, secant was equal to hypotenuse divided by adjacent. So in this scenario, in this triangle, the hypotenuse would be 1 plus x squared divided by 1. Now when you divide something by 1, that doesn't really have an effect. So this would just be the square root of 1 plus x squared. And this is what we need in order to be able to simplify the derivative completely. Arctan x was being called theta for short. Secant of theta was equal to the square root of 1 plus x squared. So secant of arctan x is equal to square root of 1 plus x squared. And therefore secant squared of arctan must be equal to that square root squared. So here's the big takeaway. The big takeaway is that the derivative of arctan is 1 divided by (1 plus x squared). I'm going to show you the technique one more time. Let's find the derivative of inverse sine. So in this case, the function that we're dealing with is the inverse of the function regular sine. We know that the derivative of sine is cos, and therefore if we take f prime, if we take cosine and replace the x with f inverse, replace the x with arcsine, if we then reciprocate that, that's going to be the derivative of arcsine. 1 divided by cosine of arcsine of x. So let's try and simplify this, and I'm going to use exactly the same technique that I used before. Previously, I set the angle theta to be a nickname for arctan. This time, I'm going to set the angle theta as a nickname for arcsine. If theta is equal to arcsine of x, then sine of theta must be equal to x. Simultaneously though, sine of any angle is equal to opposite over hypotenuse. So let's try and draw a triangle. let's try and draw a right triangle which has theta in the bottom left. Now in the tangent case, when I was dealing with opposite over adjacent, I used an opposite of x and an adjacent of 1. This time I'm dealing with opposite over hypotenuse, so I'm going to try an opposite of x and a hypotenuse of 1. That way, when I calculate sine of theta in the triangle, opposite over hypotenuse is x over 1, which is indeed equal to x. Just like last time, let's use Pythagorean theorem to fill in the remaining side of this triangle. In this case, though, one of the legs is unknown, the other leg is x, and the hypotenuse is equal to 1. So the remaining leg is given by the square root of 1 minus x squared. Move x squared to the other side and take the square root. Now before, I calculated secant of theta. This time, I'm looking at cosine on the outside, so I'm going to calculate cosine of theta. Cosine of theta is adjacent over hypotenuse. The adjacent side is given by 1 minus x squared, and the hypotenuse is given by 1. Cosine of theta is simply equal to the square root of 1 minus x squared. But theta was equal to arcsin, and therefore cosine of theta is the same thing as this cosine of arcsin. Therefore, the derivative is given by 1 divided by this quantity, root 1 minus x squared. So generally speaking, if you're trying to find the derivative of an inverse sine function or some other inverse trigonometric function, this is the process. You start out using the invertible function's derivative formula, and then the real trick is to try and simplify your result. Simplify the result ideally to something that doesn't have any trig functions in it anymore. I do this usually by nicknaming theta, letting theta represent the output of the inverse trig function, filling out a right triangle based on that setup, and then using that right triangle to figure out what cosine of arcsine would be, secant of arctangent, etc. Now, of the two derivatives that we just calculated, I think it actually is worthwhile to memorize the derivative of arctan at a minimum. This is a derivative which comes up all the time. So if you're planning to take any math courses after this is something you really want to know in your heart, that the derivative of inverse tangent is 1 over x squared plus 1. You want to be able to recognize this on sight. That concludes today's material. We reviewed the concept of a function inverse and the graphical relationship between a function and its inverse. The consequence of the graphical relationship between a function and its inverse was that the slopes of the tangent lines were related, and therefore the derivatives were related. We gave the formula which related the derivative of a function to the derivative of its inverse, and then we practiced using that specifically in the case of the inverse trig functions. Those derivatives were easy to calculate, but relatively difficult to simplify, because simplifying those derivatives required us to go back in time to some right triangle trigonometry.